Does this actually work now? Or is this still a disaster? After all of this attempting to do stuff. Is it quiet or what's the volume like? Do I need to add some gain? Or does it sound correct? Okay, it sounds normal. All right, well, okay, so I'm basically streaming from my phone through Discord. Kind of insane, but all right, let's go with it. I will try and pay attention to chat in case again. But for now, let's jump into the office hours and just pray that it does not all fall apart. But definitely yell in the chat if it does fall apart. Let me create a quick announcement, I guess, that we're actually doing office hours now. Office hours now. So what are we wanting to look at, I guess? What is the immediate questions? I remember before all of this audio insanity, someone was mentioning something like level 16. Is that what the interest is for this office hours? Actually, if I put this headphone in, I should be able to hear if my audio suddenly dies. Does that work? Oh, but then I hear myself. Never mind. That sounds terrible. Okay. Yeah, that's where I'm at right now. Okay, let's just jump into level 16 and hopefully we can get some good advice out before this setup just completely falls apart. Okay, so I guess we need to log in to my million accounts. That one. Okay. And we want to look at level 16. We will start in the teaching mode. Actually, hold on. Let me pull up the chat on my phone while I'm thinking about it. That. And chat only. Okay. Just make sure. 16. Best way to understand Yawn 85 code. Yeah, okay, so let's take a look at it. Okay, so let's start level 16. There's definitely a lot of potential strategies in terms of going about trying to understand things. Some people really like doing static analysis, basically just sitting there looking at it in IDA until things make sense. I am definitely not that type of person. I have a dynamic approach. Yeah, we'll see if there's time for like something like Baby Jail 13. If not, though, feel free to message in Discord. And I guess if no one answers in the Discord, just message me directly. Yeah, we're just gonna focus on 16 for this office hours. Hopefully some of the previous stuff has been covered in Jan's other office hours. Okay, so anyways, yeah, as I was saying, a lot of people like to look at things statically, so just sit there in IDA and just go instruction by instruction, maybe cleaning up the decompilation, trying to understand it that way. I would say that, fortunately, even though Jan 85 might seem a little crazy, it's not too complex of a program, and I think that just looking at it dynamically is actually a very valid approach. That being said, it is extremely useful to learn both static and dynamic, but I think in this office hours, I'll probably primarily focus on dynamic analysis. Okay, so if I go ahead and launch the challenge, we just hit enter, we can see an insane amount of output, at least in the teaching one. In the testing one, we don't get that level of output. But I think we can really exploit this teaching output to really accelerate our understanding of Jan 85 rather than having to do everything completely from scratch. You can use these print statements to really get a a much better understanding. Yeah, you really want to understand Yon 85. Okay, so let's look at what this is telling us. So it tells us already that it's a custom emulator. Of course, as you all know, it's emulating Yon 85. So it says you'll want to understand the emulator to understand the architecture, and the architecture to understand the code being emulated. And you'll have to understand that code to get the flag. Good luck. So it tells us this level is a full Yon 85 emulator. You'll have to reason about Yon code. Okay. So eventually, after all of that, it tells us that it's starting the interpreter loop. And we can see as it's going through, we have this VIS constantly repeating. And if we look at this, we can see, we know that this is some sort of probably minimal-ish architecture. V, it looks like, is a bunch of registers. So we have our A register, B register, C, D, and then we probably might assume that these are kind of like general purpose, because then these are just like different letters. We see S, I, and F. Maybe it's not immediately obvious what S, I, and F are. And maybe we can figure out, though, as we kind of look at this. So we can see that it's probably parsing some sort of instruction. It's saying like the opcode is 4, argument 1 is 8, argument 2 is 8. And we can see then that it tells us that this parsed instruction is doing it I equals 8. So we can see that it's doing I equals 8. We don't know maybe which one of these arguments is associated with, but we've already seen, I guess, that the first thing it's doing is an immediate instruction. Let's see here. And we can see, in fact, that this isn't a general purpose register as we were kind of predicting with this ABCD stuff. Instead, it's the I register. And we'll see now that I has been set to 8, now it's doing I is equal to 9, which is kind of interesting. Even though we just set it to 8, suddenly it's telling us that I is 9, which might be a little weird. But we will hopefully understand that as we continue looking at this, just strictly looking at this output of what it's telling us it's doing. We can see now, if maybe we just focus on these S values and occasionally reference back to the registers, we can see that D is set to E6, and then we follow that up, and D is now E6. Then we do C is 8.2, C is 8.2. Now we do some other sort of instruction, some STM, and it tells us that like star C equals D. Maybe we use some knowledge of C, and we say maybe that this is some sort of like pointer operations. Maybe it's store memory. So we're storing this D value. Let's see here. This D value, this E6, into what C is, which probably makes sense because we just set up what D and C are. So it seems like we just put this E6 value somewhere in memory, where it seems like that somewhere in memory is this 8.2. And then we do another immediate D and then C. So we're following this like DC pattern, and we store something there. And we do this DC thing again, and maybe we want to know where in memory values are being updated, assuming still that STM is like store memory or something like that. So we can see that if C is where we're storing it, in the first case we were storing at hex 82, then hex 83, and then hex 84. So it seems like we're writing some values to memory. So I guess the first thing that I'm kind of immediately curious about, just kind of completely like, you have to understand, I guess right now we're kind of looking at this black box, right? We're not even looking at the code. We're just trying to see, with the teaching help, what does it seem to imply that this program structure is doing? So maybe we could run this program through grep, and grep for all of these immediate D equals things might be interesting. So D equals E6. Yeah, let's try that. So if we grep for immediate d equals. Okay, so that gives us a bunch of values. So that's storing some stuff into memory. And then maybe we do some more command line stuff, and we do awk print, or curly brace print, the 1, 2, 3, 4, fifth thing, where it's like space terminated. This is the only way I know how to use awk. I don't really know how to use it other than do this space terminated stuff, but I know that if we pipe through grep and then pipe to awk, let's see here. We're not seeing output. Let's try 4. Maybe I messed up. No. Hold on. Let's run it. I'm wondering if there's a buffering issue here. Let's just run our output and put it to temp out. Cat temp out. Okay. And well, I guess we can get rid of that for now. Cat. Actually, we need to add it because my webcam's in the bottom right, so we'll be safe with that. Okay. Cat temp out. Okay, now we can see our values. So maybe now what we do, oops, okay. Now what we might do is take a look at what this represents in ASCII. So if we do maybe something like pipe this to Python -c print, what do we want to print? So we're going to want to take character of the hex of our input. Does that work? Sure, cannot be. No, we want to do int on that and parse it as a 16-bit thing. Okay, so that gave us. Oh, we want to do this though for each line. Okay, so we're just going to keep writing bash stuff. We could, of course, just switch to Python if that's what we're more comfortable with, but for now, we'll just show doing this in some bash, do Python, and done. Do Python -c. And we'll do this really weird. Yeah, this is a very crazy mixing of bash and Python. We're basically just trying to get the ASCII of all these values because some of these values look like ASCII. Some of them anyways. Okay, line. Do that, and finish that out. What is it complaining about? For line. Oh, we didn't do for line in. The invalid literal. Oh, it's not all caps. We made it lowercase. For line. Okay. So we can see this now. Okay. So some of this stuff is ASCII, some of it isn't. Maybe we want to also just print the original things. We'll do like that. Okay. Yeah, good enough for now. So we can see that some values seem to be loading in memory, assuming it's still following the same pattern of doing this, using the D register and C register to kind of specify where we want to load into memory, what we want to load, etc. What we can see here, maybe most of this is just some random stuff. Maybe it's interesting later on. Maybe we preloaded some very cool data in early. But we can see here something that looks actually readable. Oh, my phone just turned off. Let's make sure chat's still visible. Okay, what we can see here is this key semicolon English looking thing. So if we run the program again, so if we run challenge baby rev level 16, we will see right up here that this value that's kind of different than all of this S stuff is that it actually just printed out key to us. So very quickly, we've discovered with very basic analysis here, right? Just literally looking at the teaching output in this case. Obviously, we're going to have to figure out what we're doing for the testing mode. But if we're just trying to jump straight in and kind of extract information as fast as possible, we can use the teaching input to just very quickly see that it seems to be loading this key colon value into memory. And we saw that happen. It seems to be loading some other stuff into memory, but we can definitely tell something related to this where this is happening. If we maybe keep looking at this, so let's see here. Hold on. Why does my phone keep turning off? This is so sad. Okay. Keep trying to monitor in case there's any immediately relevant questions. But so we saw that. So we could see that this is like 4B, 4, 5. So if we go back to our grep, kind of what I'm curious about is where that gets loaded into memory at. Actually, you know what? We don't really care. Ignore that. Let's just go back to looking at this output, seeing some stuff going on. So we have all of these DC things, DC, lots of loading into memory. We're just kind of glancing through this. Store memory, immediate store memory, immediate store memory. Bunch of these things. I guess maybe if we keep looking here, somewhere we get some different things. So we can see, for instance, STK none A. It tells us pushing A. So maybe this STK stands for like stack or something. My Twitch chat just keeps cutting out. Okay. This STK seems to be some sort of stack thing because it says pushing. So maybe we've learned another operation that Yon85 can handle. It's pushing A. Stack none B. We're pushing B. Presumably before this we loaded A and B up, but maybe not. So we can see that before we pushed A was 0. So we push, and then we push B. Okay, and then we push C. So C seems to actually be something here. This C seems to be this 8F value. Just keep looking. Immediate B equals 1. Add B, S. Oh, so S is probably our stack register, so like the equivalent of RSP, just because this is close to some stack operations. And just kind of glancing at this, seeing how much we can pull out, literally just looking at the text. This doesn't seem super useful. But either way, it seems as though maybe what happens before key gets output possibly doesn't matter too much. Maybe it's just all of this code potentially, we don't know. Potentially all this code before was just responsible for making it output key colon. But then some more stuff happens afterwards. We have a bunch of stack operations. I guess we're popping C, we're popping B, we're popping A. So maybe we were pushing all of our general purpose registers because maybe we're doing some function call equivalent thing. So maybe we're using this stack because we wanted to go through and save all of our registers and then like basically call some function and then pop them back out. So maybe actually if we look back a bit, so we pushed A, B, C, and D. And then we're changing some values. So for instance, now D equals this. Stack. We push D. Push D. I guess we're doing several pushes with D here. So someone says in chat, yeah, I didn't quite get the purpose of the stack yet because the stack wasn't used in the prior levels. Suppose you might be right. The values are being saved for later use. Yeah, that's kind of just a guess because we noticed that it was pushing A, B, C, and D. And if we think of, I guess, I'm trying to think of whether or not the extent to which this would have been explored in like embryo ASM. But in general, right, if you're making a function call, if the calling convention requires that you not clobber a bunch of registers, you need to save them somewhere. And generally, the place that's going to be saved is to the stack. Hopefully, that concept isn't too foreign, but you can imagine that if you, for instance, wanted to make a bunch of recursive function calls, that you couldn't just keep clobbering registers and then return back, because now the calling function expected these registers to maybe have certain values. Now they've been clobbered and everything's a mess, so you kind of need to save them on the stack. Just going off of general calling convention standards there, just kind of guessing by looking at all of those stack pushes. Okay, but then it seems like we're doing a bunch of stack pushes with D after setting D. So like we do this immediate D equals 4B, and then we push D, and then 4, 5, and then we push push D, and then 5, 9, push D, 3A, push D, and then a space. I guess maybe it's not immediately obvious. The more you sit here and look at, I guess, hex values, you eventually come to have, similar to how with, what was it, baby eight or baby jail? No, baby, the one before. Similar to how you learned that H's are kind of this 64-bit prefix, you eventually learn that hex 20 is a space. And I guess we can show that real quick. Python. We do ord 0x or character 0x20. We see that it is a space character. So that's just something that randomly pops out to me. I figured I'd mention it. Let's see here. How do I switch back? What have I done? Did I actually lose it? Is this possible? Oh no, it's on the left, I see. Okay. So we saw this, and I'm noticing also, right? So basically, if you're curious about how do you come to realize, like, hey, am I seeing a bunch of ASCII? Basically, if you see a bunch of values that are like below hex 80 and kind of like somewhere in the middle, that's pretty alphabetic looking within ASCII. So we saw this like 4B and this 4.5 and this 5.9, and then suddenly we saw that 20 somewhere. See this 3A, we see 20. So and these are all just going, you can see they're following this structure, right? It's kind of setting our D register and then just pushing it to the stack. So it seems like similar to how at the very beginning we saw it loading up some values in memory. In this case, it's also loading up some values in memory, just in this case using the stack rather than directly specifying the address to write it to. So now we can see after this, let's see here. So we got our space, and then we pushed that, and now we're setting C. So we're breaking away from the pattern. We're setting C to 5, and then we're setting A to 1, and then we're doing a sys. So we're doing some syscall thing, probably, assuming syscall, and we see that it eventually says write, and then at that point, key pops out. So the thing that pops out to me then is that we already saw that at some point, key was getting loaded into memory using that grep through for the D register, I believe it was. And it seems to follow that this is probably our key value just getting pushed to the stack. So if we, I don't know if I can do it side by side, but we do like hex 5.9, we can see that was a Y. If we do 3A, we can see that is like a colon. Probably if we go up before this 5.9, before this, there's a 4.5 and a 4B. If we go 4.5, 4B. Yeah, so we can see this is our KEY. We kind of printed this in a weird order. This is key getting basically pushed to the stack, and then eventually we do this yawn 85 version of a syscall, and that's basically what's actually responsible for this key colon coming out. So again, we haven't even looked at the code yet. We're just kind of, in a sense, black box reverse engineering this. We're not even doing really static analysis or dynamic analysis. I mean, maybe you'd call this dynamic analysis, but really what we're doing is kind of more of a black box analysis of what's going on here. maybe just reading through, kind of trying to guess at what it's doing. Okay, so anyways, now we pop all of these registers. So maybe we just did a function call to print a string, and that function call to print a string um, it seems to have been a function call, right? Because we save these registers. So maybe we just called a function that's going to write a string. Seems okay. And now, after we're done doing these stack operations, we do this immediate B equals hex 30. And then this immediate C equals hex E. And then A equals this. And suddenly we're doing another syscall. And in this case, it's calling, I guess, the syscall read memory. And this is where our program hangs. So if we run it again, we can see it hangs here. So it seems to be reading, right? Doing some sort of read equivalent, maybe something slightly different because it's not called read, it's called read memory, but it's doing some sort of read syscall. So it's asking for input. So maybe we do, and it did say key colon. So maybe it's asking us for a key right now. So let's just put in test and see what happens. We can see at some point it did a write operation again and it said incorrect. So it seems to be some sort of key gen like thing. Okay, we have a lot of output. So we input test, and let's see what it does with that, I guess. Because basically everything going on in this architecture is being reported to us. So we do some stack operations again. Let's see here. C, B, A, and then go some, oh, we pop CBA. So maybe we just did a function call again. I don't remember if it did pushes before. And then we're setting I to 1. And then we're pushing A, B, C. And then popping CBA. So maybe we just did like I don't know why we would have done a function call that did nothing, but that's kind of sort of what it looks like. And then we're setting I again. And let's see here. And actually, since maybe I didn't explain it before, I do have to admit I already know what this I register is. But we can see, for instance, that I goes 4 and then 5 and then 6 and then 7 and then 8. It is this incrementing value that kind of happens after every instruction. This is our instruction pointer. So whenever we're doing this immediate I and setting that equal to something, that's basically doing, it seems like a jump. If it is the x86 equivalent. So we jumped to this location, this instruction here. And then we set A, we set B, so 30, 84, these seem like some weird values. C, D, and then we're adding D to I, which is kind of an interesting thing. Seems to be like a relative jump or something. Oh, maybe, would it be a relative jump? I guess we could see. Does I increase by 2? No. So maybe it's not a relative jump. Maybe taking whatever was here and then added 2 to that. So we're saving. Oh, okay. So what this seems like to me now is we're saving an instruction pointer into D. So, okay, so someone asked in chat, if setting I is a jump, doesn't that mean you need to skip instruction hex 99 to see what happened next? Okay, so you're saying you need to skip to instruction hex 99 to see what happened next. So you don't, right? This what's being reported to us isn't just all of the instructions in memory. It's a live trace of what's happening. This is actually we're kind of like living through the program. So when it did this immediate equals hex 99, now, I mean, it's going to increment by 1. Now it's already there, so it's pulling the next instruction. So for instance, if we were in a loop, right, we would see the full loop. We wouldn't just see each instruction once. If we want that, so that's kind of like the dynamic versus static analysis. probably, right, these instructions are sitting somewhere in our program, somewhere in memory, maybe like global memory. We could pull a full dump of these instructions and start statically analyzing the yon85. But right now we're dynamically analyzing the yon85, just watching the instructions go. Yeah, because you can see that I was 8 before, and now suddenly it's 9a. Okay, so anyways, what I was saying before is we do this immediate d equals hex 2, and then we do this add di. It seems like this is being saved into d. So before d was 2, and now it's a0. So we're doing like this 9e plus 2, which is getting us to a0. It seems like maybe it's saving the instruction pointer, or maybe more specifically, like 2 past the current instruction pointer to maybe account for like actually saving where we want to return to if we think of as a function call, right? Let's see here. Just a guess. And yeah, that maybe this is correct because now we see we're pushing D. Oh no, but we're not pushing them all. So maybe not, but it's saving the instruction pointer for some reason. Of course, this isn't a super important detail, and so we need to really hone in and understand what's happening. But we do see that for some reason it's saving the instruction pointer in D. Okay, so now we're setting I to 83, so we're jumping somewhere. And we're adding A and C, which were, I think, loaded before. We saw A got loaded here, C got loaded here. So we have like this 30 and then this C. And then we're adding them together, and suddenly A is now hex 3C. And then we're adding B and C, I guess. So we're incrementing, basically increase both these values by hex 8, or I mean hex C, sorry. And then D equals FF. Again, it's not super clear what's going on, but at least we're building up some intuition of stuff going on. We're getting kind of a high level view of things going on in this program. And we're not going too in detail because we're just trying to understand at some high level if anything interesting maybe pops out. So we're doing some more stack operations. Okay, so suddenly we're seeing a new instruction that we haven't seen before. We have this LDM, which seems to be, at least notationally, it's the reverse of that STM. So this seems to be like a load memory. So we're pulling from A and loading that into A, I guess. So we're pulling at hex 3B probably in memory. So we could probably figure out what is in 3B in memory if we kind of followed back. But maybe we don't super care right now. Either way, though, it's pulling something from 3B in memory, and it looks like that value that we just pulled is a 0. Okay. And it looks like we also pulled another value from memory, and that other value in memory was at hex 8F, and it seems like that value now is hex 99. So whatever's stored in memory is hex 99. And then we're doing a comparison, I guess. I'm assuming CMP is a comparison. So we just loaded 2 values from memory and we're comparing them. Okay. And we can see that this register that hasn't been changing anywhere suddenly just changed to this hex C. So this F, following from kind of just assuming this is somewhat similar to x86, we have this flags register that gets set after comparison instruction. So that got set after we did a comparison, and we kind of already know that A and B are not equal to each other because we can see right here that after A and B got loaded, one was 0, one was hex 99. We did that comparison. That got, yeah, let's see here. It compared them. And presumably, I mean, we can see they're not equal. And then some more operations happen, some stack stuff. B, we're popping B, we're popping A. So it looks like we just saved A and B, which maybe makes sense because we just modified A and B by loading them. And then we do, let's see here. We set D to 97, and then we jump ND. Don't know what this N is, but D is this 97. Maybe this N has to do with what kind of jump we're doing. Maybe like jump not equal, or I don't know what N might be, but we know before we were doing immediate I for doing jumps, and now we're seeing an actual jump instruction that we haven't seen before. So it seems like maybe this is some sort of, as a result of the comparison, right, we're doing a conditional jump, a conditional branch, and it's telling us, in fact, right, this is taken. Okay, so that means probably, since we just set D to 97, we're probably going to be executing at 97, or close enough, 98, one off. Okay, and then we're doing some more pushes, pops. C equals 0. We're comparing D and C, so maybe it's interesting to see D and C. So these don't seem to be equal. Okay. Not taken. Uh-huh. And at this point, I feel like I've been looking through these instructions forever, so now I'm kind of getting bored of looking at these instructions. Maybe I'm going to look through this a little bit faster. If there's any questions, feel free to ask in chat. We're just looking strictly at the output here to kind of understand Yon 85 without even looking at the code. Add B, add S. Okay, we're pushing. So we're loading up, we seem to be loading memory again, right? We're doing this pattern that we've seen in the past where we do an immediate D and then we do a stack operation and then an immediate D and then we push it. So maybe if we look through all of these immediates, kind of skip through, know that pattern, probably what we just did is we did like a puts of incorrect, right? Because we saw this pattern, we probably can, if we wanted to confirm that, we could confirm that the memory is getting pushed to the stack with this incorrect. But it seems like now we've kind of hit the end of our program. So hopefully in your mind, as you were looking at this with me, you saw those comparisons. Those comparisons are kind of pivotal. If we imagine that this program is something that's asking for a key, we randomly input the word test, and then it just tells us incorrect. And somewhere in the middle there, between saying asking for the key and taking our input and then outputting incorrect, it did some comparison operations. Those in my mind jump out as kind of this critical component. So if we, let's see here, if we go back to that, or maybe we'll just grep actually. If we grep compare, we put in test. So we see that, maybe we want to look back a bit. I think if you do like -A3, you'll see the 3 things before the compare as well. Maybe it's the 3 things around the compare. We can see here that so we know that A and B are being compared. We can see here that A is 0. We can see here that B is hex 99. And then we saw another comparison happen, I guess, where D is C and hex C, that is, and that the C register is 0. Okay, so again, so we have this program where we are receiving a key and then it's telling us incorrect. So if you think about it like a program, right? If you're just sequentially executing instructions and at no point you're doing like comparison operations, it doesn't seem like it's a very interesting program. Comparisons are kind of like where the logic of the program really comes down into play, right? You do a comparison and then you're going this way in the program, or maybe you're going this way in the program. So this comparison really jumps out as being really important here. So we saw this, and now I'm wondering, so we know that it did a syscall to read memory. So if we actually look back at that as well, sys, we can see it's doing sys hex 8d. So maybe either this hex 8 probably corresponds to the syscall number, or assuming there is a concept of a syscall number, but probably there is because we've seen multiple things use that. And then it uses D. It's not super clear what this is, but maybe we say test again. We get the comparison. So we read memory, and then we see return value in register D. So it seems like in register D is 5, which is the length of our input if we include that new line character. So I guess this is probably specifying where to put the output, or where to put the result. That seems definitely different than x86. The result always ends up on RAX. Here it seems like it's telling us it's deciding to put it in D, which is 5, which we know, okay. This is probably the syscall number, which means our arguments are probably coming in through these registers. So it seems like if we look at A, B, C, and D, one of these probably corresponds to how much data it's willing to read. And if we look at this sys hex 2D and it says write, we can see here that it's similar. How long is the word incorrect? Probably hex B. So if we think of like the read and write syscall in x86, where there's a file descriptor, and or I guess in Linux, where there's a file descriptor, and then there's a location in memory, and then there's a length, it seems to follow the same. Or maybe one, this is their standard out. Maybe we're writing from location 6 in memory, and we're writing 11 bytes out. I think incorrect is probably 11 bytes. So it probably follows here that we're reading into hex 30, and we're reading hex E many bytes. So maybe we want to increase that test. So someone's saying likely that hex 5 return and register D for the syscall. It's because test is 4 bytes plus a null terminator. So it might be there would be a null terminator, but possibly maybe it's automatically converting our new line character like into a null byte. But then I would probably more likely guess, I mean, we'd have to look deeper into this, that fifth character is our new line character. Okay, but so it seems to be reading a longer input. So let's give it a longer input. So rather than just giving it test, let's give it A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. Hopefully that's long enough. We can see eventually it tells us command not found. So we definitely gave it something that was long enough. And now if we look at this, oops. Oh, now we're still looking at incorrect. Let's copy this. We want to get rid of the last two. Rather than grepping for the syscall, let's grep for the compare. Give it that. Okay, so before we saw like a 0 and a 99 or something. Okay, now this is no longer the case, right? So we can see we have a 6C and a 99. So if we look in our IPython and we do ord of hex or character of 6C, I think it was, we get the letter L. Did we send it the letter L? Why can't, okay, there we go. Did we send it the letter L? It looks like we did right here. So maybe if we change that L, so maybe instead of L, we do Z, M-O. Can we see this change? So now we see this is a 7A compared to 99. We do 7A. We see that's our Z. So it seems to be comparing seems to be comparing against what we're giving it here. So maybe we need to change this up. We want to echo NE that, and maybe we want to change this Z with hex 99. What did I just do? KZM, okay, yeah. Okay, so if we give this now, what did I just do? Oops. And we pass that. Okay, now what happens? So now we can see our first comparison is comparing this hex 99 with this hex 99. So this is now different, right? So maybe it was interested in if it was less than, or if it was equal to, or if it was greater than. But certainly not equal. It probably has changed the logic. And we can see that now there's more comparisons involved. So for instance, let's see here. So we do comp AB, and before we had another comp CD that followed. So where C is hex B and D is 0, I guess. I'm not super sure what that would be because we know that the characters we've given it don't really line up with hex B. But we can maybe ignore that for now because we can see that, in fact, we have two more comparison operations that have occurred. I guess one thing we could do is, so this is, it's comparing C and D. So this is B and Z, or yeah, so this is hex B and this is 0. So if we change this back from being 9, 9 to be like maybe 9, 8, so it's no longer equal. So we can remember this was B and 0. And now it is 0 and C, I guess. Oh, no, C and 5. So this has definitely changed that comparison. It's not super immediately obvious, but either way, we can tell that now we're doing another comparison, and we're comparing 6B with 4, 5. 6B is K. So if we look here, K is just before that value that is we're setting as hex 99. So now if we change this to hex 45, I guess, because that's what it's comparing it with. And we don't necessarily know if, so it's saying, it's telling us that our key was incorrect, and it seems to still be saying that. I guess we'd have to confirm, but we don't know whether we want it to be equal or not be equal, but we can imagine just it's doing this comparison. If we just invert the result of what that comparison is, we're going to be going down a different program trace, probably. So now we have more comparisons. So we had A, B, C, D, A, B, C, D. So maybe we can look at these CDs. We can see C here was B0, and now it's A0. So this just went down by 1. So this value is decreasing. AB. Let's see here. Yeah, so it's definitely decreasing. Okay, but either way, we could keep doing what we're doing since we seem to be getting a longer and longer program trace. So now at this point, it's doing a 6A with 5C, so that if the previous one, that's probably our J, we're probably going backwards right now. Let's confirm that, 6A is our J, yep. So if we change that to be a 5C, okay, so now we're comparing these. We had 6A before? Yeah, 6A. So now we're down one more. And it's comparing it with FF. Okay, oops. XFF. again. So let's see what the next comparison is. We want B1. Maybe at this point, we can see a pattern in that our trace is getting longer and longer with every value we put in. So we can see this B1. We do XB1. Oops. Okay. And now we can see an A6. And I would consider automating this, but we're almost there, and this would actually be somewhat of a tricky thing to automate. I think we can do it faster by hand. A6. Yep. And then a 5-9. And then a C5. And then a D0. Almost there. Figure we might as well finish off this comparison chain. And a 2E. And a 3-1. And a C4. Okay. And now what's happening? So before we were doing all of these A-B comparisons, and then we were doing like a C-D, and the C is getting smaller and smaller with each iteration of this, it seems. Now we finally got them to be equal. So C and D are equal, and I guess C and D are equal again. So we currently have a grep right now. If we get rid of this grep, let's see if it says something other than incorrect. And as a matter of fact, it does say something different than incorrect. It tells us the flag. So hopefully this was useful to understand how maybe like a completely different approach to solving this challenge. And you might think that maybe this approach of solving it is dumb because it isn't going to work on the testing one, right? If we launch the testing challenge, I can tell you that it's not going to be telling you all of this ISV stuff. But in doing this approach, we've actually learned a lot about how Yon 85 functions. And if you think back to embryo GDB, there's no reason you couldn't figure out how to get GDB to report all of these values to you. Now, that's going to require some static analysis of the program to kind of understand what it is that's causing this A, blah, B, blah, C, blah, D, blah, to be output to us. And we would basically need to now use GDB to here, I guess we can show you what it looks like in 61. So remember, right, we have this VIS stuff. If we go to the testing variant and we click on start, and we click on workspace, just to make sure my audio is still good, right? Just so I can test. Am I hearing myself? Yeah, I am. Okay, just making sure. Let's see here. If we now launch the challenge, show you. So you might be thinking, this was great, but it does not at all help us with the testing mode because the testing mode does not allow us to use this black box sort of technique, quasi-dynamic, quasi-black box technique. But in fact, you can figure out how to make it do this. So if we look at IDA, so I currently have level 16.0 loaded up. If we go to main, and we just go to decompilation, we can see a bunch of outputs. We can see eventually it calls interpreter loop, tells us this starting interpreter loop. You can see it does interpret instruction. So we can see right here that it's telling us this is where that print statement is occurring. It's telling us that A is equal to this formatted thing based off of this value passed in here, this A1. So this 1024, 1025, 1026. we can recreate this using GDB scripting. We can use GDB scripting to get all of this information back to us. So we can see here that it's using 1024, 1025, 1026, 27, 28, 29, 30. So this seems to be, I guess, where the registers are located in memory. And it might change, but hopefully this idea makes sense. So we might have to do a bit more analysis. So for instance, something that jumps out to me is, let's see here. Should we go back up one to this interpreter loop? So we can see that this one is doing A1 plus 1029 and it's increasing it by 1. So an interpreter loop would constantly be changing the saved instruction pointer, or not the saved instruction pointer, but the instruction pointer. So that was 1029, and we can see that this follows up here. So if this is no longer at 1029, we can figure out that it is what value it is by going here and seeing that it's doing A1 plus 1029. So we know that this must be the I register. So for instance, now if we switch to the testing mode, how do I do that? File, open, okay. Open the testing one, overwrite, sure, whatever. And we jump to main. And oops. Go to decompilation. We go to this thing. We can see it, and it doesn't change. We can see that this plus 1029 is still here. And if we jump in here, what we could do now is we could take this A1 using GDB scripting and then do that plus 1029 to it and print that out and say, hey, this is our I register. And you could follow this up to basically do GDB scripting to recover all of that teaching output if you find that useful. And clearly it was useful because we could use just that teaching output to kind of slowly figure out what the flag was. Obviously, now we know the structure of the program, and maybe there's a simpler way to do it. But yeah, getting those values is incredibly useful. Are there any questions related to this? If there are, please state it, and we can kind of dive a little bit into that. Let's see here. So I guess maybe I'll show you how we could get that instruction pointer real quick. So we can see that this is where it's happening, this function right here, which, how do I make this show what we want? I think this. Okay, so this plus 1A72. If we do GDB start I, actually, so something we want to show, since it's a SUID program, so there's a couple of issues here. Because it's SUID and because it's stripped, it's a little bit trickier to use GDB scripting here, but it is in fact possible to use GDB. Something you're going to want to do is you're going to want to copy the challenge binary. So if we copy it, so basically, so it's no longer stripped. So we have this here now. If we do GDB on this version, or it'll still be stripped, but it'll no longer be SUID. And since it's no longer SUID, GDB will actually be able to correctly disable randomization. Okay. So if we do start I, and then we can't break main, but we can break. So here's a quick way that you can kind of get GDB functioning. Actually, I'm going to switch to using GDB scripting right away. And let's see why. Just that way we have everything reproducible. x.gdb. And yeah. Okay, so we want to do start I, and then we want to break somewhere we can break that we can't break at main, but we can break at libc start main. We lost the chat. Yep. We can start at libc start main, and then we can continue. So if we run this, oh, I guess we have a pending breakpoint. I don't remember exactly how to deal with that. Hold on. No. Set pending breakpoint pending GDB set pending breakpoints. There's a way to do it. Let's see here. this, set breakpoint pending on. Okay, maybe we'll do that before the start. Okay, let's rerun, and I'm going to actually run it with batch mode, dash batch. Okay, so we can see that we braked at libc start main, and once we're there, we can actually break at main because there's going to be this symbol defined main, and that's where main actually is. So now we can break at main, we can continue. We'll actually be broken finally at main. Main not defined. Actually, do I need $sign main? I might need $sign main. No. Well, we can definitely do RDI because this is the first argument to main. So if we break at RDI, not confused. Oh, I think I need a star. I think that's the issue. I need to do B star main. Let's try that. I don't remember this GDB syntax. Okay, yeah. So we hit that second breakpoint. So now we're actually broken at main. And what we can do now is we can break at where we actually want to break. Actually, in fact, we didn't need to do all of this. This is just showing you, I guess, how you can magically break at main, even though it's a stripped binary. We'll leave it in. We can instead do set base equals this. We need to change a couple values. Base equals this. We need to change that to 0, 0, 0. I think this needs to be a 4. So now what we can do is we can do break base plus this value, 1A72, 0x1A72. So we didn't actually need to do all of that breaking at main stuff, I think. It says it's pending. We'll probably have something wrong here. Then how do we do this? I remember, I've seen Jan do this. I just don't remember exactly how he used this base stuff. Do we need like wrap it in parentheses and put a star or something? Yeah, we do. Okay, nice. Or we can just put a star there according to the chat. Let's try that. Okay, yep. So we're breaking here. We're hitting this breakpoint. And I guess now what we could do is we can actually do like commands and we could do x8i RIP. And before I forget, we should set disassembly flavor Intel because I don't actually have a GDB in it, I believe. X8i, and I think we need to continue here because we're currently in batch mode, which does some weird things. Commands. Why is that not printing to us? Let's try getting rid of the batch. Where am I? So that works. What am I doing wrong here? Is it? I mean, we can see we're breaking at the right points. Then what do we want? Why am I not getting my stuff here? Printf test. Oh, it's probably because I never hit continue here. I think that needs to happen. I think. Oh, but we already did break main, so we need to get rid of here. That. Okay, I think this is going to work. Maybe. Hold on, let's just get rid of all of this. We don't need it anyways. Oh, we never did start. We'll do a run at the end now. Did we not do start I? We need to do start I also. Start I, set up our breakpoint, run. That's what we want. Okay. So we're hitting this a bunch of times. So that's cool. Actually, what we want to do now is do registers, and then we want to do like I, percent, X, and then let's see what it is. So we were saying that it's going to be this A1 plus 1029. So plus 1029. We do RDI because it's our first argument being passed in, A1 RDI, and then we do our, I already forgot, plus 1029 plus 1029. This right here might not be exactly right because we need to dereference this. So how would we do that? If we convert this to a, well, it should be just a single byte. So if we do like an uns, or I think we can do uint 8t star, probably make some more room so it's easier to see this. And wrap this all in parentheses. And it looks like something that could work. We probably want to get rid of this. But we can see something that's working. And actually we want to add silent here so that we don't get all these breakpoint messages. And now you can see that we're starting to build up the teaching output, right? We've just now recovered this I register. In fact, I think I could do 0, 2 to make that slightly better. Just because I saw something pop out. Yeah. So we can see, right, that it's actually not so crazy to do that solution that we did on the teaching mode, because we've kind of figured out what the program does and some information that we're actually really interested in. And now we can just start using GDB scripting to recover that information. So right now we're recovering the I register. We could start, really anything. We could recover all the other registers. We could recover all of memory. We didn't exactly use that though, so we could just recover what the instruction is that's about to be executed. And we were really interested in specifically comparison instructions. So we don't exactly know which one is the comparison, right? So we're currently, if we remember back to the teaching, we saw that this was like interpret instruction. So we know that probably one of these is the compare instruction. And maybe it's not super easy to see which one it is, but probably there's going to be some sort of comparison going on in the decompilation. This is doing a lot of stuff. V2, blah, blah, blah. Let's just look at all of them. So maybe one of them will jump out as a comparison. Nope. Not jumping out. Not jumping out. This has comparisons. If V3 is less than V4, if V3, so this looks like a comparison. We're getting less than, greater than, and equal to. So we can see here that this is doing a comparison. Remember, we discovered while we were doing the teaching version that we really care about comparison operations because certainly in the case of this relatively small program, comparison operations are kind of like directly linked to what our input is. And it's really easy to see how our input relates to a comparison. And then we can start inverting whether or not the comparison goes through. So this one looks kind of promising. So we can see, just to be sure though, let's be complete. 166, just in case multiple of them look like comparisons. No, not really. I think that other one looked really good. Oh, this looks like our syscall thing. Okay, let's go back to, is it this one or the next one? Next one. So, A2, doing something with A2. A1, A2, V3, V4. It definitely looks like compare. Someone in chat is agreeing that it's compare. Question is, I guess we could break in this function. Let's do that. So if we want to break, so basically right now I'm trying to figure out how do we know which two registers are being compared. And I guess in fact we already know where all of our registers are, so maybe we don't even care. Maybe we'll just print all the registers and we'll see, using our knowledge from teaching, what looks cool. So this is plus 166. So we don't know exactly which is which, but so for instance, we can see 1030 is being used as an offset here. I mean, we could just kind of guess, I guess. Or we could go back to the teaching mode one. Maybe that's easier. Go back to teaching, and that would actually confirm whether or not that is the compare, if it looks structurally similar. If we go here, override care. If we do interpret instruction, did I type that right? I did. Somewhere we have an interpret compare, and this looks basically exactly the same. So I guess it's doing some sort of describe register. Oh, this is here. Okay, so this tells us what's being compared, and then it does a read register. So now we know what those functions were. But I guess if we go back to interpret instruction, we could see all the offsets that were for our registers. So it's 1024 through 1030. So if we want to just print that, maybe here we print that we're doing a compare, and that's all we print. And then maybe up here, print all of our registers. And someone says in chat, comparing the teaching and testing code is what I've been abusing. I question whether it will continue to be valid in future modules. So this course doesn't get too deep, I guess, in reversing. So I would say it probably will be sufficient. Obviously, in the case of just general purpose, being able to reverse engineer, you're not always going to have kind of a version with all the symbols and tons of useful like debugging messages necessarily, and you'll have to do it from scratch. But hopefully it makes sense that you could, in theory, do this all from scratch. It would definitely be a much bigger pain, but it could be done. 1028, 1029, 1030. Okay. B, C, D, and then we have SIF. SIF. B, C, D. S. So someone said, sorry, I missed a bit. Where did you get 1024 offset? So we are just looking at the teaching variant where it's basically printing out all of our registers. And we can see that it's going off of this A1 value and just referencing in 1024, 1025, 1026, etc. And these are all 8-byte value, or 1 byte values, 8-bit values. SIF. Okay. So now if we do this again, and we run it. So now we can see all of our registers as we go along. I guess we haven't gotten to a compare yet. If we put in A, B, C, D, F, G, H, I, J, K, L, M, N, O, P. Here's sourced. Oh, this needs to be fixed. Okay, let's do it again. G, Okay, so it says incorrect. We can see a compare just happened. So it would happen under this set of this set of registers. So something in here is being compared. And I don't completely remember from other version what it was. I mean, our input is probably this 3B. Was it being compared? Maybe 7, 9? Was it A and B? 6C, if we switch back to 6C. Or I guess what we can do is we can just send a bunch of A's to confirm that 6.1 shows up somewhere. Compare. Oh, the previous, I was looking at the second compare. Yep, so this is our 6.1. So we know that our input's somewhere in there. We're probably comparing with this AF, if I had to just kind of guess. We could go back to the teaching one. I just don't remember which register it was. But clearly we have kind of reconstructed enough of the teaching output to give us what we want in order of kind of recovering the key. So hopefully that makes sense. All right, I'm going to start wrapping up this office hours. If there's any more like quick questions, feel free to ask. Let's see here. How did you determine to use star uint8 underscore t star as the variable for the register? Okay, so I think you're talking about this right here, right? So we know that yon85, at least from the teaching, was all just like single byte values, 8-bit values. So what I'm doing here is I'm taking RDI, and the reason I'm taking RDI is because it's this A1 thing. The very first thing being passed in is RDI, and it's going off of that. It's adding 1024. That's what it's equivalent to just add 1024, right? Because it's a single byte value. You know that. And so I'm just adding the 1024. I'm casting it to a uint8 underscore t pointer, wrapping it all in parentheses, and then dereferencing it to get the value. That's what that is. I mean the type. Yeah, so we just know, I guess, the type from the teaching mode where we saw that everything was working in single byte values. If we had noticed that something had jumped up to being more than a byte, we could, of course, increase this accordingly, but it seems to be the case that we only care about a single byte. And we can also see that here, that this is a single byte value, and it's just grabbing a single byte, right? It's just pulling that out. So that seems to also confirm that. Okay, any more quick questions? Otherwise, I'm going to end office hours. And obviously, feel free to ask more questions on the Discord. All right, I don't see any more questions. Yep, ask in the Discord if there are more, and good luck. Hopefully this was at least somewhat useful in a kind of another approach. You've probably seen dynamic analysis, you've seen static analysis. I am a huge fan of, I guess, what I call black box analysis, which is kind of use the program. Obviously, in this case, teaching output is very helpful for doing black box analysis. It basically becomes dynamic analysis, but yeah, okay. So thank you for watching.